My name is Halima, and this project is on cat and dog audio classification. Let's jump right into it. Let's start off with a little bit of an introduction. This is a supervised learning binary classification task. It is binary because it is either a cat audio or a dog audio. I sort of arbitrarily chose 1 for dog audios and 0 for cat audios. I also used 3 models: the k-nearest neighbors, support vector machines, and convolutional neural network models. My original goal was to achieve an accuracy of 90% at the very least. Let's talk about the dataset now. The dataset that I chose was sourced from Kaggle and is called Audio Cats and Dogs. It contains 164 wave files for cat audios and 113 wave files for dog audios, making 277 files overall. Here's an example image of an audio signal of a cat meowing. I will go ahead and play this audio for you now. Okay, that was a very obnoxious cat. Let's keep going. Here's an example image of an audio signal of a dog barking. I will now play this audio for you. Wonderful! Let's talk about the data preprocessing that I did for the support vector machine and k-nearest neighbor models. The library that I will be discussing the absolute most is the Librosa Python library. This library works really well with audio data. I started off by using librosa.load to load the audio files. I then extracted the MEL frequency cepstral coefficients using librosa.feature.mfcc with 17 coefficients. I then took the average of all of those coefficients and stored them in a list for each audio file. I then put those lists into a pandas data frame. This pandas data frame had 17 features for the 17 coefficients and 277 rows for the 277 audio files. I then split the data 80% and 20% for training and testing, respectively. Now I will talk about the data preprocessing that I did for the convolutional neural network model. Convolutional neural networks work really well with image data, so I wanted to create spectrograms, which is a visual representation of a signal's frequency components over time. I basically converted all of the audio data into image data. I then used librosa.feature.mel spectrogram to create spectrograms from those MEL frequencies, which I talked about in the previous slide, and converted those values to decibels using librosa.power2dB. This returned image data. Each of those images were various shapes and sizes, so I converted them to be 224 by 224 pixels. I then normalized all of the images by dividing by 255. I then saved each file spectrogram as a PNG file and put it into a directory to be used later. Here are example images of both a dog audio and a cat audio, which were turned into spectrograms. As you can see, these two images are very different, which I thought would be very helpful in the classification task. Next, let's talk about model selection. There were the 3 models that I chose: KNN, SVM, and CNN. I chose to work with k-nearest neighbors because this is a classification task, and also k-nearest neighbors has very few hyperparameters to tune. I also chose to work with support vector machines because this is a binary classification task, which support vector machines do very well. They are also very computationally efficient, especially in comparison to convolutional neural networks, which is the last model. I chose to work with CNNs because I knew that I could convert the audio data to image data. And I thought it would be really cool to use a neural network for this project. Next, let's talk about the KNN model. I chose the number of neighbors to equal 2 because this is a binary classification task. This gave me an accuracy of 88%, which is very, very close to my goal of 90% accuracy, which is really good. I didn't end up doing any hyperparameter tuning on the KNN model because the number of neighbors won't change. Next, let's talk about the hyperparameter tuning that I did for the SVM model. I started off with the kernel type being the radial basis function and the C value being 1000. This gave me an accuracy of 84%. The reason why I chose this as my initial model was because I was basically copying and pasting from code that I had done for an assignment. Then I used grid search to tune certain hyperparameters such as the kernel type, the C value, and the gamma value. This gave me the best accuracy that I have for this model, which was 88% with a C value of 1, the gamma being scale, and the kernel being RBF. These are the default parameters for the scikit-learn SVM model, which was intriguing to me. Now let's talk about the hyperparameter tuning that I did for the CNN model. My initial architecture for the CNN model had 3 convolutional layers with their associated 3 max pooling layers. I also had the categorical cross entropy as the loss function, and I had 2 neurons in the output layer. After I ran this with 10 epochs, this gave me an accuracy of 89%, which is very, very close to my goal of 90%. After some researching, I changed the loss function from categorical cross entropy to binary cross entropy, as this is a binary classification task. I also changed the learning rate to 0.001 to improve precision during gradient descent. And lastly, I changed the number of neurons in the output layer from 2 to 1. This gave me an accuracy of 59%, which is much worse than I had previously. I think the main culprit of this was the learning rate being adjusted, so I will discuss this in future slides. After a bit of confusion, I went back to having some previous hyperparameters. So I changed back to having categorical cross entropy for the loss function. I also changed back to having the default learning rate, and I changed to having 2 neurons in the output layer instead of the 1. The only thing that I truly changed from the very first iteration was the number of epochs. Originally I had 10 epochs, which gave me an 89% accuracy. I then changed this to 20 epochs to see if it could just push me over to 90%. However, this ended up giving me an accuracy of 82%, which is worse, and I was a bit confused by this. When I saw what was printed to the console for each epoch, I realized that at about 15 epochs, it reached an all-time high of a 92% accuracy before somehow getting worse. So when I reran the model with 15 epochs, I got an accuracy of 92%. Which was the highest I was able to achieve with the CNN model. I have some thoughts on this CNN model. As you can see, here is an example of the model accuracy graph and the model loss graph. The training data for the model accuracy graph has 100% accuracy, and the model loss graph for the training data shows that the training data has 0% loss. This is unusual, to say the least, and my thoughts are that potentially the CNN model is overfitting to the training data. One reason why this could be is because this could be too small of a data set with the 277 files, and thus it is not great for computer vision tasks. Overall, I think that the model is struggling to generalize, and I am uncertain on how to fix the model to get it to generalize better. I'd love to hear your thoughts. Next, let's talk about results and evaluation. As you can see, I have printed off the confusion matrix for each model. The KNN and SVM model both had an 80% accuracy, or 88% accuracy, and they have the exact same confusion matrix with the exact same numbers. The CNN model has a better accuracy. However, given what we just talked about in the previous slide, and how the CNN model might be overfitting to the data, I think that it would be wiser to trust the results from the KNN and SVM model more than the results from the CNN model. And with that, that is the end of my presentation. Thank you so much for listening.